When you look at the night sky, you can see thousands of stars with nothing but your eyes when you're far from city lights. In fact, there are many more stars in the sky that are too faint for us to see. Every single star you can see is a part of our Milky Way Galaxy, our celestial home that has captured people's attention for ages. The shimmering band of stars, dust, gas, and dark matter that makes up the night sky draws us in. All these elements are held together by gravity. As we navigate through the cosmos, an intriguing enigma emerges. What is the Milky Way truly like? What is it made of, and where does our solar system exist within it? Astronomers have pondered these fundamental questions for many centuries, and finding answers has not been an easy task. Yet, beyond its luminous beauty lies a tapestry of mysteries waiting to be unraveled. Join us today as we embark on an amazing adventure around the Milky Way, uncovering its mysteries, wonders, and majesty. You're probably somewhat familiar with our solar system. If nothing else, you probably already know that it contains 8 planets in addition to Earth, the Sun, moons, and several other celestial bodies like asteroids and Pluto. However, there is much more beyond the solar system that you may not be aware of. From Earth, we can see roughly 6,000 stars without the use of a telescope. Even though that seems like a large number of stars, it represents a very small portion of the total. In fact, for every star you can see, there are more than 20 million that you cannot see. The majority of stars are either too dim, too far away, or obscured by clouds of cosmic dust. While the Milky Way Galaxy contains all of these stars, there are other larger galaxies as well, including the Andromeda Galaxy. Every galaxy is a system made up of various stellar remnants, interstellar medium, and star systems. Astronomers believe there are 100 billion galaxies in the cosmos, yet they are not certain. Intergalactic space, which contains a thin gas, lies between the galaxies. Given the size of our solar system and the fact that it is only one of many in our galaxy, it is understandable why the universe is thought to be infinite. This truly helps put into perspective how tiny both Earth and humans are in the big picture. Through the use of radio and X-ray telescopes, scientists have been able to gather information over the past century about the composition of the interstellar medium. They have shown that it is made up of extremely diffuse ionized hydrogen atoms, dust, and cosmic rays scattered throughout thick gas clouds that are thought to be the birthplace of new stars. But because of the Sun, all 8 planets, and a far-off disk of debris known as the Kuiper Belt, its precise nature just outside our solar system has remained mostly unknown. The Kuiper Belt is located between 30 and 50 astronomical units from the Sun. 1 astronomical unit is equivalent to the distance between Earth and the Sun. The heliosphere, a massive protective bubble created by the solar wind, surrounds everything in our solar system. This bubble acts like an invisible shield, buffeting against the interstellar medium and keeping out most dangerous cosmic rays and other material. As the Sun and its surrounding planets hurtle across the galaxy, without the heliosphere, life would certainly have evolved differently, or maybe not at all. The area where the Sun's magnetic bubble ends and weakens is known as the interstellar space border. The heliosphere is a magnetic bubble filled with plasma or ionized gas. The solar wind, which pulls magnetic field lines away from the Sun, blows material into the heliosphere with its own magnetic fields and charged particles. The plasma in the interstellar medium exerts an inward push on the edge of the heliosphere, creating a complex and dynamic structure there. When the solar wind encounters interstellar space, it begins to weaken and slows to approximately 62 miles per hour, having previously traveled between 370 and 430 miles per hour. The termination shock is the point at which this happens. The heliosheath is the area in the heliosphere where the solar wind continues to slow down after the termination shock, while the heliopause is the outermost point of the heliosphere. The solar wind stops and gives way to interstellar space at the heliopause, which is located around 11 billion miles or 18 billion kilometers from the Sun. Since the beginning of human space exploration, only 2 probes have made it to interstellar space, the area outside of the solar system. After launch in 1977, Voyager 1, the first spacecraft, took more than 30 years to reach the heliopause, a limit that scientists believe marks the beginning of interstellar space. It was an amazing accomplishment, sending back vital information via a medium unaffected by the Sun. As we exit the solar system, we will reach Alpha Centauri, the closest star system to Earth, located about 4.37 light-years away in the constellation Centaurus. It is a triple star system consisting of 3 stars, Alpha Centauri A, Alpha Centauri B, and Proxima Centauri. Alpha Centauri AB is a binary star system made up of Alpha Centauri A and B, which are Sun-like stars classified as spectral types G and K, respectively. These 2 main stars have an apparent magnitude of -0.27, making them appear to be a single star to the unaided eye. Only Sirius and Canopus are brighter than it, making it the brightest star in the constellation and the 3rd brightest in the night sky. Alpha Centauri B is smaller and cooler than Alpha Centauri A, with 0.9 times the mass of the Sun and less than 0.5 times its luminosity, while Alpha Centauri A has 1.5 times the luminosity and 1.1 times the mass of the Sun. The 2 stars have a 79-year orbital period around a shared center. The distance between A and B fluctuates from 35.6 astronomical units, AU, or roughly the distance between Pluto and the Sun, to $11.20, or roughly the distance between Saturn and the Sun, due to the eccentricity of their elliptical orbit. In the Alpha Centauri system, Proxima Centauri is the star nearest to the Sun, located approximately 4.2 light-years from Earth. Robert Innes, a Scottish astronomer, discovered the star in 1915. Proxima Centauri is a red dwarf star, which is the most common kind of star. It is roughly 7 times smaller than the Sun and a little more than half as hot, at 3,100 Kelvin. On the other hand, our Sun is 5,772 Kelvin. As a matter of fact, this little star is just 50% larger than Jupiter. Red dwarf stars have long lives because they consume hydrogen fuel very efficiently. Proxima Centauri is expected to remain in its current state for more than 4 trillion years. Although the Alpha Centauri system can be seen in the constellation Centaurus, Proxima Centauri is usually not visible to the human eye. Proxima Centauri orbits the other 2 stars in the system, Alpha Centauri A and B. Proxima Centauri takes 550,000 years to complete an orbit of A and B. With an apparent visual magnitude of 11, Proxima Centauri is the dimmest of the 3 stars. This star emits light at a slower rate than the Sun, with a luminosity of just 0.17% that of the Sun. However, Proxima Centauri is categorized as a flare star, which is prone to massive solar flares because its brightness can vary by more than 1 magnitude in a matter of minutes. These flares, which occur multiple times a day, have the potential to be powerful enough to make Proxima Centauri visible to the human eye. The greatest solar flare ever observed in the Milky Way Galaxy was released by Proxima Centauri in 2019, glowing 14,000 times brighter in ultraviolet wavelengths than normal. Even though Proxima Centauri will live longer than the Sun, it will eventually meet the same fate. Proxima Centauri will end up as a white dwarf star because it does not have the mass to turn into a neutron star or a black hole when its hydrogen supply runs out. As of 2022, astronomers have detected 3 planets orbiting Proxima Centauri, Proxima B, C, and D. These are the closest planets outside the solar system. Red dwarf stars are small and cool, so planets can orbit quite close to them and still be classified as being in the habitable zone. This is the range of distance from a star where a planet's water, if any, could be liquid and potentially support life. Proxima Centauri B was discovered in 2016 and is estimated to have about 177% more mass than Earth, making it likely to be a rocky planet. Proxima Centauri B is still within Proxima Centauri's habitable zone, despite being much closer to its star than Earth is to the Sun. It orbits Proxima Centauri every 11 Earth days at a distance of about 0.049 Australian dollars, over 20 times closer to Proxima Centauri than Earth is to the Sun. Proxima Centauri b is most likely tidally locked, like our Moon, with one side always facing its star. Given its proximity to its star, it is possible that liquid water exists on the opposite side, but its habitability is uncertain due to the extreme radiation and flares from its host star. Proxima Centauri b feels the gravitational pull of its star much more strongly than we feel the tidal effects of our Sun here on Earth. The Moon exerts more tidal force than the Sun on Earth because it is closer. And tides don't just pull on the oceans, they can also move air. It's possible that the tidal pull on the atmosphere of Proxima Centauri b is up to 500 times stronger than that on Earth's atmosphere. It's likely that Proxima Centauri b is getting close to the maximum tidal force that a planet can withstand while still retaining a solid surface. However, Proxima Centauri b's climate and weather are mostly unaffected by its extremely high tides. Situated just outside the habitable zone at around 1.5 astronomical units from the red dwarf is the mini-Neptune exoplanet Proxima Centauri c, which is around 7 times the size of Earth and orbits its star once every 1,900 Earth days. First thought to have been discovered in 2019, this super-Earth or mini-Neptune appears to shine much brighter than expected for its size, indicating that it may be shrouded in dust clouds or surrounded by a ring system. Astronomers estimate the planet's temperature to be extremely cold, probably close to -233 degrees Celsius, making it uninhabitable due to its distance from its star and large mass. The gravitational pull of Proxima Centauri c caused its parent star's velocity to wobble, leading to the star's initial detection in 2019. In 2020, pictures from the Hubble Space Telescope from 1995 were used to confirm Proxima Centauri c's existence. It is therefore one of the rare exoplanets with visual confirmation. A third planet was discovered in 2022 around Proxima Centauri. The exoplanet, known as Proxima Centauri d, orbits its star at a distance of roughly 3% of Earth's distance from the Sun and has about 25% of Earth's mass. Every 5 Earth days, Proxima Centauri d completes one orbit around its star due to its close proximity. It is among the lightest exoplanets that scientists have yet observed. Furthermore, in 2021, scientists detected what may be the first indications of an exoplanet orbiting Alpha Centauri A, also known as Rigil Kentaurus. In the star's habitable zone, called Candidate C1, it is estimated that C1 has a mass between half of Saturn's and Neptune's and orbits Alpha Centauri A at a distance of roughly 1.1 Australian dollars. Using direct thermal imaging, C1 was found with an elongation of around 0.1 arcseconds. It appears to be as bright as a giant planet, which is consistent with the orbital motion of a planet in a 70 degrees orbit. The fact that C1 is situated in the habitable zone of Alpha Centauri A and may be a mini-Neptune or super-Earth makes the discovery of this exoplanet even more intriguing. We are almost certain that planets similar to Earth exist in Alpha Centauri, but the main question is, could humans ever actually live there? The most challenging obstacle in our quest to set up a new home in the Alpha Centauri system would undoubtedly be traveling a huge distance to reach these 3 stars. Even though Alpha Centauri is the nearest star system to Earth, it is still more than 4 light-years away, which is roughly 23.5 trillion miles or 37.8 trillion kilometers. We would need a much faster spacecraft or another means of transportation to cover such a great distance. NASA claims that the Space Shuttle Discovery, which was discontinued in 2011, had a top speed of about 17,500 miles per hour. Still, reaching Alpha Centauri would take more than 148,000 years at this constant speed. NASA estimates that even when the Orion spacecraft, the crew capsule linked to the Artemis program, is ready to carry people, its maximum velocity will be approximately 20,000 miles per hour. This won't significantly reduce the travel time to Proxima Centauri, especially since these vehicles are designed for relatively short trips to the Moon or Mars, rather than journeys out of the solar system. As we've discussed, the only spacecraft to make it out of the solar system thus far are Voyager 1 and Voyager 2. Even at their top speed of over 35,000 miles per hour, it would take them nearly 40,000 years to travel 2 light-years to reach the indistinct boundary between Proxima Centauri and our solar system. This implies that it might take these spacecraft more than 880,000 years to get close to the star. After all, it takes light more than 4 years to reach Alpha Centauri. A spacecraft needs to be extremely tiny and robotic to reach a distant star in a reasonable amount of time, like within a generation. Furthermore, it still needs an incredibly strong energy boost to get up to speed. That is the basic concept behind the Breakthrough Starshot project. By creating a light sail-equipped nanocraft called Starship that would be sent into Earth's orbit. The mothership would release the tiny probes one at a time, which would then ride the beams of a colossal ground-based laser array. The main challenge, though, is the Earth's atmosphere, which distorts lasers and incoming light and makes it challenging to apply the force required to move a spacecraft forward. Much more potent lasers on the ground would be able to keep a close focus on the space mission, thanks to small lasers mounted on satellites that would evaluate atmospheric impacts in real time. To send out the vessel at any given time, the required lasers need an astounding 100 gigawatts of power, which is equal to the total U.S. electricity usage. However, the lasers only need to operate for 10 minutes at full power. They plan to employ 100 million lasers to distribute the electricity across an area of 1 square kilometer. The Starshot team is determined to push the boundaries of space exploration. When the lasers are switched off, the object racing through space will be traveling at a stunning 20% of the speed of light. More than 130 million miles per hour or 216 million kilometers per hour. With a diameter of just over 10 meters, this spacecraft could reach Alpha Centauri in about 22 years. However, it might be significantly slowed down by the Sun's gravitational pull and interstellar debris. It will take 4 more years for the spacecraft signals to reach Earth, even if they make it to Alpha Centauri. Alpha Centauri is moving toward Earth very slowly and doesn't pose an immediate concern. The distance between Alpha Centauri and Earth as of 2024 is approximately 3.26 light-years. It will be at its closest in 29,700 AD, when it will be about 3 light-years away. Over the course of a human lifetime, the slow change in distance will have no noticeable impact on Earth or the solar system. Space is a remarkable place, and we are learning new things about it every day. Leaving Alpha Centauri behind, we travel on to Barnard star, the second nearest star to the Sun at a distance of 5.95 light-years. It is named after Edward Emerson Barnard, the American astronomer who discovered it in 1916. With an estimated age of 11 to 12 billion years, roughly twice that of the Sun, Barnard star is an old star and most likely a thick disk member of the Milky Way. Red dwarfs that are young or middle-aged often spin fast enough to produce powerful magnetic fields, which can result in flares that quickly double a star's brightness. However, Barnard star was too old to show this kind of behavior. On July 17, 1998, Diane Pearson and her colleagues at NASA's Goddard Space Flight Center revealed that a flare similar to this one had been released by Barnard star. At the time, the star's spectra were being obtained using the 2.7-meter telescope at McDonald Observatory by William Cochran of the University of Texas at Austin. His hope had been to find alterations that would indicate the existence of planets in orbit. Instead, he saw emission lines in the spectrum, which showed that the star might be flaring. 4 years later, Cochran's team's investigation revealed that the star's hot blue flare was similar to those from younger red dwarfs, even though it was quite old. The temperature of the flare was at least 8,000 Kelvin, which is more than twice as hot as the 3,100 Kelvin temperature of the star itself. As Barnard star gets closer to us, its distance from Earth is decreasing by 0.036 light-years every century at an incredibly fast speed of 108 kilometers per second, or 67 miles per second. Its closest approach to the Sun will be at a distance of just 3.85 light-years by 11,800 AD. In terms of its proper motion, Barnard star is also the fastest-moving star in Earth's skies. Another feature that makes Barnard star unique is its large proper motion of approximately 10.4 arcseconds per year, which is equivalent to the diameter of the Moon every 180 years. Because of this and its relative proximity, it is an ideal target for exoplanet searches since any systematic variations in its motion across the sky caused by orbiting planets would be more noticeable. Finally, a planet was found around Barnard star in 2018. The planet orbits the star at a distance of roughly 60 million kilometers, 37 million miles, on a 233-day orbit and has a mass at least 3.2 times that of Earth. The planet is not in the habitable zone due to the star's low brightness, and any water on its surface would probably be frozen. As we move farther away, around 8.6 light-years from Earth, near the constellation of Orion, we find Sirius, the brightest star in the night sky. Sirius, also known as the dog star or Sirius A, is the brightest star in Earth's night sky. With a mass twice that of the Sun, Sirius has a diameter of 1.5 million miles, 2.4 million kilometers. If positioned next to our Sun, Sirius would outshine it by more than 20 times. Located in the Canis Major constellation, Sirius is a binary star. The star's name comes from the Greek word siros, which means glowing or scorching. With a surface temperature of almost 18,000 degrees Fahrenheit, Sirius has a bluish tint and is 25 times brighter than the Sun. It is clearly visible in the winter night sky of the northern hemisphere. The ancients were familiar with Sirius due to its extreme brightness. However, astronomers were surprised when Sirius B, a companion star, was discovered in 1862. Sirius B is visible to the naked eye, however, it is 10,000 times fainter than Sirius A. Thanks to data from the Hubble Space Telescope, astronomers were finally able to estimate the mass of this faint object in 2005, despite it being extremely difficult to observe from Earth. Within 20 light-years of the Sun, there are around 131 objects, including stars, brown dwarfs, and sub-brown dwarfs. Only 22 stars are bright enough to be seen without a telescope, meaning their visible light must have an apparent magnitude of at least 6.5, the lowest brightness that can be seen with the naked eye from Earth. The known 131 objects are found in about 94 stellar systems. Out of these, 103 are main sequence stars consisting of 23 typical stars with higher mass and 80 red dwarfs. In addition, scientists have discovered 21 brown dwarfs, 1 sub-brown dwarf, WISE J085510.83-071442.5, which is possibly a rogue planet, and 6 white dwarfs. White dwarfs are stars that have used up all of their fusible hydrogen. A red dwarf candidate known as Scholz's star and its companion brown dwarf passed near the edge of the Oort cloud around 70,000 years ago. At this moment, it is approximately 22 light-years away from the Sun and has likely triggered a comet storm that will take over 1 million years to reach the inner solar system. The orbits of Kuiper belt objects were affected by its passage. Some other stars, such as the G-type star HD 7977, have also been studied. HD 7977 made a close pass around 2.8 million years ago and is currently located about 247 light-years from Earth. Of course, past interactions aren't the only thing to consider. There will be more stars in the future. In the next 15 million years, 694 stars are predicted to approach the solar system at a distance of less than 516 light-years. Based on data from the Gaia telescope's second data release, 26 of them are likely to arrive within 3.3 light-years, and 7 more within 6 light-years. Due to the sheer number of stars that must be surveyed, this number is probably much higher. For example, a star that was approaching the solar system 10 million years ago would be 600 to 6,000 light-years away from the Sun today, whereas millions of stars are now closer to the Sun. GJ 710 is one of the most well-known examples of a close future passage. It is an orange star around 60% the size of the Sun, located in the Serpents constellation. This star is heading in our direction at a speed of 5,499 kilometers per hour, or almost 32,000 miles per hour. In 1.29 million years, it will pass the Sun at a distance of around 10,520 Australian dollars, astronomical units. That's over 100 times the distance to Pluto, which orbits the Sun at an average of 39 Australian dollars and 50 cents, but it still has the potential to disrupt the solar system. If humans are still around on Earth at that point, we don't have to worry about any disruptions to our orbit. If GJ 710 has any effect at all, it might only have an impact on the outer solar system. It shouldn't have any impact on anything within 40 astronomical units. But it could possibly cause disruptions to the Oort cloud because it has a very high probability of passing through it. For millions of years, comet showers would result from that heading toward the Sun. This might lead to roughly 10 comets visible to the unaided eye every year. Searches for stars that are close to the Sun could not only be an opportunity to find ancient comets, but also to predict an intriguing future for observers on Earth millions or even thousands of years from now. The local interstellar cloud, which is around 30 light-years across, is where the solar system and other stars and dwarfs are now moving within or close to. The local interstellar cloud is in turn contained within the local bubble, a cavity in the interstellar medium about 1,000 light-years across with an odd peanut shape. Our Sun was far away when the bubble first formed 14 million years ago, but about 5 million years ago, the Sun's path made its way into the bubble. Interestingly, stars form on the surface of the bubble but not inside it. There are 7 star-forming regions around this bubble. Because of this local bubble, life has become possible on Earth. Today, as we go farther away, we reach the Orion constellation, around 1,344 light-years away from Earth. 1 light-year is the distance light travels in a single year, about 6 trillion miles or 10 trillion kilometers. The Orion constellation is one of the 88 modern constellations and is named after a figure in Greek mythology. It contains over 60 stars, including Betelgeuse, a red supergiant star located around 650 light-years away. This is one of the largest known stars, with a diameter of about 767 million miles, 1.2 billion kilometers. It's about 700 times the size of the Sun and has a mass between 10 and 20 times that of the Sun. Because Betelgeuse may have less than 300 years of fuel left in its core, there has been continuous discussion around the world about whether or not it will explode. The star's core will collapse into a black hole as it burns through those final drops, blasting out the star's outer layers at speeds of up to 25,000 meters per second or 40,000 kilometers per second. Astronomers refer to this blazing demise as a supernova explosion, and in Betelgeuse's case, it will be a breathtaking sight for observers on Earth. Those layers of gas and dust will shine in our sky for several weeks, comparable in brightness to the full moon. Because the star is only 650 light-years away from Earth, the issue is that most astronomers do not think Betelgeuse is quite ready for a big explosion just yet. Astronomers normally expect that it will blow up in the next 100,000 years or soon on a cosmic time frame, not a human one. The other famous stars in this constellation are in the line of Orion's belt, which consists of 3 stars located around the middle of the constellation Orion. These are Alnitak, Alnilam, and Mintaka, from east to west. The belt is perhaps the most recognizable feature of Orion because it is visible all around the world. These 3 supergiant stars are each thousands or tens of thousands of times brighter and several times more massive than the Sun. Despite these stars appearing close to one another in the sky, they are actually light-years apart. Orion's belt is mainly used by astronomers as a celestial landmark when searching for M42, also known as the Orion Nebula. M42 is located below the belt and is one of the most visible Messier objects for beginner astronomers, as it is easy to locate and view with a telescope or pair of binoculars. Looking at it is like looking into a celestial nursery where new stars are born. One of the largest gas and dust clouds in our Milky Way Galaxy is the Orion Nebula. It is approximately 2 million years old and located about 1,300 light-years away from Earth. Because the magnificent nebula has an apparent brightness of +4, it is even visible to the human eye. On the astronomical magnitude scale, +6 is the faintest object that is visible under the best lighting conditions. This massive nebula, which has a diameter between 30 and 40 light-years, could be giving birth to 1,000 stars. Within the nebula is a young open star cluster whose stars are still only loosely connected by gravity after forming together in the gas cloud. This cluster is sometimes called the Orion Nebula Star Cluster. An international group of astronomers suggested in 2012 that this cluster in the Orion Nebula might have a black hole at its heart. Through small telescopes, you can see the 4 brightest stars in the Orion Nebula, known as the trapezium. The Orion Nebula is illuminated by the light of these young, hot trapezium stars. In terms of star lifespans, these stars are young, having an age of approximately 1 million years. An infrared picture of the Orion Nebula was taken by the James Webb Space Telescope last year. It shows an explosion of dust, stars, and clouds in red, purple, and blue against a background of dark space. Additionally, 540 planetary mass objects with masses ranging from 0.6 Jupiter masses to Jupiter itself have been discovered by James Webb within the nebula. Among these planetary mass objects, the most fascinating are the Jupiter mass binary objects, which are not separate objects orbiting in space by themselves. Our Milky Way galaxy is a spiral galaxy. A spiral galaxy looks like a flat rotating disk with a bulge in the center and spiral arms extending outward from the bulge. While there are many minor arms and just 2 major arms in our spiral galaxy, astronomers used to believe that there were 4 major arms. Scientists have found that just 2 arms wrapping off the ends of a central bar of stars dominate the Milky Way's beautiful spiral structure. These discoveries were made possible by NASA's Spitzer Space Telescope using infrared imagery. The 2 major arms of the galaxy, Scutum Centaurus and Perseus, are visible at the tips of a thick central bar, while the 2 now demoted minor arms, Norma and Sagittarius, are situated between the major arms and are less distinct. Although the minor arms are mainly made up of gas and areas where stars are forming, the major arms have the highest densities of both young and old stars. Large telescopes are used by radio astronomers to study the motions of those hydrogen clouds that trace the arms. With a pitch angle of around 9 degrees, the Perseus arm has a spiral extension, measures over 60,000 light-years in length and 1,000 light-years in width, and contains the well-known Crab Nebula, in addition to double clusters. On the other hand, the Scutum Centaurus arm is around 55,000 light-years in length and 1,000 light-years in width. Our solar system lies between 2 prominent spiral arms, the Perseus arm and the Scutum Centaurus arm. However, we are not completely free-floating in empty space. We are situated on the edge of the Orion Cygnus arm, sometimes referred to as the Orion arm or local arm, which is a small spiral arm. This spiral arm spans about 10,000 light-years in length and 3,500 light-years in diameter. However, a 2016 analysis indicates that its length may exceed 20,000 light-years. The Orion arm is named after the Orion constellation. The solar system is located in the local bubble on the inner edge of the Orion arm, 26,000 light-years from the galactic center, halfway down the length of the Orion arm. You might be surprised to hear that the Sun takes 250 million years to complete one rotation around the Milky Way. This is referred to as a cosmic year or galactic year. Thus, during its lifetime, the Sun is estimated to have completed only 18 to 20 orbits. Since the beginning of mankind, the solar system orbits the Milky Way at a speed of about 220 kilometers per second, or 0.73% the speed of light. At this speed, the solar system takes around 1,400 years to travel 1 light-year or 8 days to travel 1 astronomical unit. Following the ecliptic, the solar system is traveling toward the zodiacal constellation Scorpius. The last time the solar system was in this position in the Milky Way, there were still dinosaurs on Earth. Who knows when it will happen again? Humanity might be extinct, or it might have evolved into something else entirely. Our place in the galaxy is important because it seems that galaxies have habitable zones just like planetary systems. Because many of the Milky Way's stars orbit the galaxy along paths that take them through the deadly spiral arms. An astounding 95% of them may not be able to support habitable planets. Radiation from the crowded stars is deadly for any star that goes through one of these stellar swarms. To maintain its alignment with the galaxy's rotation, our solar system orbits sufficiently far from the galactic center to stay in the comma region between the spiral arms. Within a large and intricate galaxy, the Earth and its planetary siblings are well situated in a quiet, resource-rich region. As we move closer to the center of our Milky Way Galaxy, roughly 9,500 light-years away from Earth in the Scutum constellation, we will reach Uy Scuti, considered one of the largest known stars. It has a radius of 1.18 billion kilometers, which is 1,700 times larger than the Sun's radius. This gives the star a diameter of over 8 astronomical units, equivalent to 8 times the distance between the Earth and the Sun, or about 150 million kilometers, 93 million miles. Because of this hypergiant star's immense size, its outer surface would extend well beyond Jupiter's orbit, which is about 5 times farther from the Sun than Earth. The gas nebula ejected from the star stretches 400 times the distance between Earth and the Sun, far beyond Pluto's orbit. To put it in perspective, more than 1 million Earths could fit inside the Sun, but about 5 billion suns could fit inside a sphere the size of Uy Scuti. Not surprisingly, Uy Scuti is classified as a hypergiant star, a classification that comes after supergiant and regular giant. Although it may be the largest in size, it is not the heaviest or most massive star. The term mass in massive refers to the amount of matter in the star. The heaviest star is our 136A1, which weighs about 300 times the mass of the Sun but only has about 40 times the Sun's radius. On the other hand, Uy Scuti is significantly larger than the Sun, although it has only 7 to 10 times the Sun's mass. Similarly, being so massive doesn't mean that Uy Scuti is very hot either. In fact, its surface is almost half as hot as our Sun's. Another thing that makes Uy Scuti particularly interesting is that it's a variable star. Over time, variations in luminosity can be seen as a result of the material's continuous fluctuation at and near the surface due to the unstable battle between the forces of gravity and fusion. These stars are of special interest to astronomers because they can shed light on the inner workings of stars. Although Uy Scuti, like many other stars, is thought to be capable of supporting a planetary system, it's possible that the innermost exoplanets have already been swallowed by the host star's expansion. Furthermore, Uy Scuti is so faint that it is improbable we will ever be able to witness those exoplanets directly. As we approach the center of our Milky Way Galaxy, about 26,000 light-years away, we see a celestial enigma, Sagittarius A star. This supermassive black hole is an incredible cosmic monster that is beyond understanding. Sagittarius A* is no ordinary black hole. Its estimated mass is a staggering 4.3 million times that of our Sun. Imagine compressing millions of suns into a single point, a gravitational singularity where space and time warp beyond recognition. This massive monster is located at the heart of the Milky Way, our spiral galaxy. A black hole is a region of space so densely packed with mass that nothing can escape from it, not even light. A black hole is invisible to us, but telescopes can detect the material surrounding it. The surrounding matter, which can consist of gas and dust, heats up and releases detectable radiation. In some cases, telescopes can observe the gravitational influence of a black hole on the motions of nearby stars. Observing it directly is a formidable challenge, as Sagittarius A* is obscured by a dense layer of dust that prevents optical observations. However, astronomers have developed smart strategies to break through this cosmic curtain. The Event Horizon Telescope, EHT, a network of radio telescopes spanning the planet, made history in April 2019 when it successfully obtained the second-ever image of a black hole. This discovery came after the EHT collaboration released the first picture of M87, the black hole at the center of the farther-off Messier 87 galaxy. In 2019, Sagittarius A* was visible in the photograph as a dim outline against a brilliant background. This turbulent region, known as the accretion disk, feeds matter to the hungry black hole, causing occasional X-ray flashes. Despite Sagittarius A* being less massive and more than 1,000 times smaller than M87, the two black holes look remarkably similar. Its surrounding gas disk, which stretches out over a distance of 5 to 30 light-years, can reach temperatures of up to 18 million degrees Fahrenheit, 10 million degrees Celsius. Not only is the supermassive black hole at the center of our galaxy spinning, but it's doing so at nearly maximum speed, consuming everything in its path. Physicists use NASA's Chandra X-ray Observatory to study the X-rays and radio waves coming from material outflows to measure the rotational speed of the supermassive black hole in the Milky Way. A black hole's spin speed is represented by the letter A and ranges from 0 to 1, where 1 is the maximum rotational speed for a specific black hole, representing a significant portion of the speed of light. Physicists discovered that Sagittarius A* rotates at a speed of 0.84 to 0.96, which is near the upper limit determined by the size of a black hole. The spin of a black hole differs from that of other celestial bodies. Black holes are truly regions of spacetime defined by an outer, non-physical boundary called the event horizon, beyond which no light can escape. Unlike planets, stars, and asteroids, which are solid objects with physical surfaces, black holes spin in such a way that they literally distort spacetime itself, dragging anything inside the ergosphere along with them. This phenomenon is known as frame dragging or the lens-stirring effect, implying that understanding a black hole's spin is necessary to comprehend how space behaves around it. Additionally, frame dragging around black holes produces strange visual effects. As light approaches a rotating black hole, its path gets twisted or curved due to the rotation of spacetime, causing a process known as gravitational lensing, where the gravitational pull of the rotating black hole bends the path of light. Frame dragging effects can result in the production of light rings and even the shadow of a black hole. These are examples of how light is affected by a black hole's gravitational pull. The theoretical top speed of a black hole is determined by how it feeds on matter and thus how it grows. As matter falls into a black hole, it increases the black hole's spin, but there is a limit to how much angular momentum it can possess. The black hole's mass is another factor. The gravitational attraction of more massive black holes is stronger, making it harder to spin them up. This could explain why the rapidly feeding supermassive black hole at the center of galaxy M87, the first black hole ever captured on camera, is spinning at between 0.89 and 0.91, despite having the mass of 6.5 billion suns. Meanwhile, Sagittarius A*, with a mass equivalent to about 4.5 million suns, has a spin speed between 0.84 and 0.96. However, something strange happened while researching this black hole. Some scientists believe that Sagittarius A* may not be a black hole after all. Instead, it could be an immense concentration of dark matter. Imagine a dark pool of invisible matter forming the basic structure of our galaxy. Sagittarius A* has never been directly confirmed, despite the fact that it is widely believed to be a black hole. To put it simply, it is an extremely bright radio emitter located at the Milky Way's galactic core. The astronomy community encountered a challenging problem when the G2 gas cloud moved a bit too close to Sagittarius A star. The G2 gas cloud just kept drifting without undergoing any notable changes, despite the fact that a supermassive black hole should have pulled it in and destroyed it. Observing the interaction between Sagittarius A** and the G2 gas cloud revealed that G2 was not an ordinary gas cloud, as seen by the lack of effect. Scientists explained that at least two components had to be present to allow the cloud to pass that close to the black hole without being devoured. One is an extended cold and low-mass gas cloud, and the other is a very compact segment like a dusty object that dominated the detected emission from G2 as it passed by. However, astronomers may be more concerned with the possibility that Sagittarius A* is not actually a black hole. Initially, scientists created a simulation of our galaxy because they were intrigued by the idea that the Milky Way center might actually be a mass of dark matter. Researchers found that despite replacing the galactic center, the Milky Way Galaxy still exists and operates in basically the same manner throughout the simulations. The behavior of the rotating curve in the Milky Way's outer halo was identical to that of nearby S stars or those connected to the radio source Sagittarius A star. Taking their inquiries a step further, they proposed that darkinos, a family of particles related to fermions, may comprise the mass at the center of the Milky Way. Apart from their extreme features, such as devouring everything around them, if darkinos clump together into a massive object, they would have the same properties as a black hole. Sagittarius A* is mostly dormant and only occasionally absorbs gas or dust, yet it has an estimated mass millions of times that of our Sun. Although there are still many unanswered questions concerning the supermassive black hole, future observations from the Event Horizon Telescope should help shed light on these mysteries. Stellar mass and intermediate mass black holes form when massive stars cease nuclear fusion and can no longer support themselves against complete gravitational collapse. The mechanism that forms supermassive black holes like Sagittarius A* is unclear because there are no stars large enough to directly collapse into a black hole of this size. There are two possible explanations: either smaller black holes emerge to form larger black holes, or smaller black holes grow enormously large by consuming gas and dust from their surroundings. Sagittarius A* remains an astronomical marvel, a cosmic mystery at the heart of the Milky Way. As our understanding deepens, we continue to unravel our galaxy's secrets. Structure of the Milky Way. In 1917, American astronomer Harlow Shapley provided the first reliable measurement of the galaxy's size. He determined the size by first determining the spatial distribution of globular clusters. Contrary to what had been previously believed, Shapley discovered that the galaxy is enormous, with the Sun closer to its periphery than its center, rather than being in a relatively compact system. Assuming that the globular clusters surround the galaxy, he calculated that the galaxy has a diameter of roughly 100,000 light-years, or 600,000 trillion miles. The Sun is located approximately 30,000 light-years from the galaxy's center. His values have held up remarkably well over the years. The Milky Way's stellar disk is roughly the size predicted by Shapley's model. Dark matter, or invisible matter, may fill an even larger volume than expected, while neutral hydrogen is somewhat more widely distributed. According to recent calculations, a dark matter area that includes a few visible stars might have a diameter of about 2 million light-years. In addition to having multiple satellite galaxies, the Milky Way is a member of the Local Group of Galaxies, which is a subcluster of the Virgo supercluster, which itself is a component of the Laniakea supercluster. There are at least 100 to 400 billion stars in our galaxy and at least that number of planets. The Milky Way and everything else in space are in motion. The radiation from the Big Bang, known as the cosmic microwave background, is used as a reference point for calculating the speed of objects in space. The Milky Way Galaxy is thought to be traveling at a speed of roughly 600 kilometers per second or 372 miles per second within the Local Group of Galaxies. Since the oldest stars in the Milky Way are almost as old as the universe, they most likely formed shortly after the Big Bang's dark ages. The galactic nucleus is the site of a wide range of activity, apparently powered by the black hole. The region emits X-rays and infrared light, and it is possible to see fast-moving gas clouds there. Data clearly show that matter, including some gas from the Z direction that is perpendicular to the galactic plane, is being drawn into the black hole from outside the nuclear zone. As the gas nears the black hole, the central object's strong gravitational force squeezes the gas into a rapidly rotating disk, which extends outward about 5 to 30 light-years from the black hole. Surrounding the nucleus is an extended bulge of stars that is nearly spherical in shape and consists primarily of population II stars, though they are comparatively rich in heavy elements. A star's metallicity, or the amount of elements heavier than helium in its composition, divides stars into three primary population groups. Population III stars are the oldest, and population I stars are the youngest, like our Sun. The disk portion of the galaxy contains population I stars, with ages ranging from 0 to 10 billion years. The spiral arms house the younger stars. The orbits of population I stars are well organized, following roughly circular paths in the galactic disk's midplane. Young star clusters made of population I stars are called open clusters because the stars are loosely bound together, in contrast to the old, concentrated globular clusters. Compared to population II stars, population I stars have a higher abundance of elements heavier than helium, which astronomers often refer to as metals. The oldest population I stars have somewhat eccentric orbits, carrying them up to 3,000 light-years from the disk plane, with a metal abundance 0.1 times that of the Sun. Population II stars, on the other hand, inhabit the spheroidal components of the stellar halo and bulge, with masses of less than or equal to 0.8 solar masses. Being old, their ages range from 10 to 13 billion years. Their orbits are more randomly oriented than population I stars and are highly elliptical. As a group, the spheroidal component has little overall rotation. Population II stars are found in globular clusters, which helped astronomers locate the center of the galaxy, as these clusters swarm around the galactic center like bees around a hive. In contrast, population III stars have not been directly observed. They are believed to contain virtually no heavy elements and are thought to be the first stars that formed in the primordial universe shortly after the Big Bang. These stars were extremely massive and hot, burning their fuel rapidly to create heavier elements from hydrogen and helium. When they died, they exploded as supernovae, scattering some of these elements into space. Population III stars are believed to have created the first heavy elements that became part of later stars, playing a key role in the formation of the first galaxies. Numerous globular clusters of related stars are mixed with these stars, and both the stars and clusters orbit the nucleus almost radially. Our galaxy is surrounded by a massive hot gas halo that stretches several 100,000 light-years in diameter. This halo is a spherical cloud of stars surrounding the galaxy, with a mass roughly equal to the total mass of all the Milky Way's stars. Astronomers have proposed that the Milky Way's halo is composed of two populations of stars. Findings from the Paranal Observatory indicate that the stars in the inner halo are 11.5 billion years old, while the outer halo is thought to consist of stars from smaller galactic systems. Stars in the halo are older and have lower metal content than most of the stars in the Milky Way's disk. The halo also contains gas and dark matter, serving as evidence of two galaxies that collided billions of years ago, reinforcing the idea that the Milky Way has a dynamic origin story. In the Milky Way's stellar halo, astronomers have found more than 200 distant variable stars known as RR Lyrae stars, which are important standard candles used to measure astronomical distances and are often found in globular clusters. The farthest star from Earth is about 1 million light-years away, nearly halfway to the Andromeda Galaxy. Approximately 90% of the matter in our galaxy is dark matter, which is invisible to the human eye, while stars make up the remaining 10 to 15% of the visible matter in the Milky Way, which is primarily composed of gas and dust. Simulations of gas and dust in the Milky Way's rotation have shown that the large amount of dark matter creates an invisible halo. Without dark matter, the stars in the Milky Way would orbit much slower than observed. The Milky Way's dusty ring can be seen in the night sky on a clear night. Because we are located about 26,000 light-years from the center of the Milky Way, we cannot capture an image of the disk in its entirety. Any depiction of our galaxy that you've ever seen is either an artist's rendering or an image of another spiral galaxy. We don't have a full picture of the Milky Way because we can only capture images from within the galaxy. So, why do we believe that the Milky Way is a barred spiral galaxy? There are several clues. The first clue about the shape of the Milky Way comes from the bright band of stars that stretches across the sky in areas with dark night skies. This band of stars can be seen with the naked eye and is the result of viewing the disk of stars that make up the Milky Way from inside the disk, indicating that our galaxy is mostly flat. Many telescopes, both on Earth and in space, have taken photos of the Milky Way's disk by capturing a series of images in different directions, similar to how you would create a panoramic photo with your phone or camera. The concentration of stars in a band further supports the evidence that the Milky Way is a spiral galaxy. If we lived in an elliptical galaxy, the stars of our galaxy would be spread out across the entire sky instead of concentrated in a single band. Early theories about the Milky Way suggested that the galaxy was only a few thousand light-years wide until about a century ago, and most people believed it was the entire universe. Even though other galaxies had been discovered, it was thought that they were only small objects within our own galaxy. French astronomer Charles Messier discovered the first galaxies in the 17th century, though he didn't realize what they were at the time. As a skilled comet observer, Messier noticed several additional fuzzy objects in the sky that he was certain were not comets. To help other comet hunters avoid similar confusion, he created a list. Messier's list included 110 star clusters and spiral nebulae, which were denoted with an M followed by a number, such as M51. It took astronomers nearly 300 years to understand these fuzzy spiral nebulae. Some astronomers argued that these nebulae were island universes, or objects similar to the Milky Way that existed outside of it. Others thought that these spiral objects were gas clouds within the Milky Way. The debate continued until the 1920s, when American astronomer Edwin Hubble measured the precise distance to a spiral nebula. In 1923, while studying the Andromeda Nebula, now known as the Andromeda Galaxy, Hubble discovered a Cepheid variable star within the nebula. The connection between a Cepheid star's luminosity, its brightness, and its period, the time it takes for the star's brightness to vary, had first been identified in the early 1900s by American astronomer Henrietta Leavitt. This relationship, now called the period luminosity (PL) relationship, allows astronomers to calculate the true brightness of a Cepheid star by determining its period, which can be observed by measuring changes in its brightness over days or weeks. Hubble used the PL relationship to determine that the Cepheid star he was observing in M31, the Andromeda Nebula, was located outside of our own galaxy. This finding settled the debate over spiral nebulae and proved that they were, in fact, distant galaxies similar to the Milky Way. Hubble continued to study galaxy distances using Cepheid variables and published his findings in 1929. In his work, Hubble created a graph showing the distances to galaxies using Cepheid variables and their velocities, which were determined by estimating the redshift of their spectra. Most galaxies are moving away from us or receding, as indicated by this graph. Hubble found that the rate of recession, known as the recessional velocity, is directly correlated with the distance from us, that is, more distant galaxies recede more quickly than nearer ones. This relationship is now known as Hubble's law. Initially, Hubble's estimates of the recessional velocity were very high because, at the time, astronomers did not know that there were several types of Cepheid variables, each with slightly different period luminosity relationships. As astronomy advanced, the value of the graph's slope, known as Hubble's constant, was refined. Today, the accepted value is around 65 kilometers per second, meaning that galaxies recede by an additional 65 kilometers per second for every megaparsec they are away from us. There are trillions of galaxies in the universe, each containing up to a few 100 billion stars. Just as studying atoms helps us understand the properties of materials, studying galaxies helps us comprehend the universe. Understanding how galaxies form and evolve is crucial to our understanding of the cosmos. While the study of galaxy formation began around 50 years ago with the work of Egan, Lynden-Bell, and Sandage, we still do not fully understand this process. Many details remain to be explored. Observing galaxies other than our own provides insights into the evolution of the universe. However, the only galaxy for which we have extensive data on individual stars is our own, the Milky Way. Other galaxies are simply too distant for detailed star-by-star observations. Nonetheless, understanding the Milky Way offers significant insights into the broader universe because approximately 50% of the stars in the modern universe reside in galaxies similar to the Milky Way. The Milky Way's history and development are a microcosm of the universe's evolution. Soon after the Big Bang, about 13.61 billion years ago, the Milky Way began as one or more small overdensities in the mass distribution of the universe. These overdensities became the seeds for globular clusters, where the oldest stars in the Milky Way formed. Approximately half of the Milky Way's material may have originated in other, distant galaxies. These stars and star groups now form the Milky Way's stellar halo. As the Milky Way's mass increased, it began to rotate more rapidly, compressing its interstellar medium into a disk-like shape. This disk became the site for later generations of star formation. Over its history, the Milky Way has consumed many smaller galaxies, gradually growing to its present size. Cosmological simulations suggest that over the last 12 billion years, the Milky Way has merged with more than a dozen smaller galaxies, including a particularly massive galaxy called the Kraken, which merged with the Milky Way approximately 11 billion years ago. Even today, the Milky Way is consuming the Canis Major dwarf galaxy, adding its stars to our galaxy's spiral. Currently, the Milky Way is moving toward the Andromeda Galaxy at a speed of 250,000 miles per hour. It is expected that the two galaxies will collide in roughly 4.5 billion years. The Milky Way and Andromeda are the two largest galaxies in the local group and, due to their mutual gravitational attraction, they are bound to merge. Before dark energy became dominant, these galaxies became gravitationally bound to each other. This merger is expected to dramatically change the night sky over Earth. The Milky Way is currently orbiting a point in space roughly halfway between it and the Andromeda Galaxy. Although it may be hard to believe, experts think that our solar system will likely survive this massive event. This is because galaxies are mostly made of empty space, so the collision will not have a significant impact on our solar system. Despite both galaxies containing around 100 billion stars each, they are still very far apart. Andromeda is currently located 2.5 million light-years away from Earth. Similar to how a falling object accelerates as it gets closer to the ground, Andromeda will be pulled closer and faster towards the Milky Way as their gravitational forces increase. In about 4 billion years, the Milky Way and Andromeda will begin a violent interaction, tearing at each other. Eventually, the distinct shapes of these two spiral galaxies will be lost. The cosmic destruction will continue until the supermassive black holes at the centers of both galaxies collide and merge. By this point, neither the Milky Way nor Andromeda will remain as separate spiral galaxies. Instead, they will form an entirely new type of galaxy, an elliptical galaxy, which will be the new home of our solar system. But what about life on Earth during this time? Well, in approximately 7.5 billion years, the Sun will expand and become a red giant, swallowing the Earth. This will mark the end of Earth's existence. However, long before that, within about 4 billion years, solar radiation will gradually increase, causing Earth's surface temperatures to rise. This could trigger a runaway greenhouse effect, similar to what is currently happening on Venus, making it unlikely that life on Earth will survive long after the merger. That said, it's possible that by then, humanity will have developed the technology for space travel and may have already left Earth and the solar system. Perhaps we will be able to witness the collision of Andromeda and the Milky Way from a different vantage point in space. As we contemplate this cosmic event, it serves as a reminder of how brief our lives are in the grand scheme of things. We are made of stardust, watching an unfolding cosmic story. For whatever reason, we are here now, sitting and pondering the universe. We, the children of the universe, born from simple elements over billions of years, now look in awe at the endless darkness of space and wonder about it all.